Hello, my name is Stefano and I work at KS Geisler in Gothenburg, Sweden. And in this talk I will talk about adding H support to the NOEL-V microprocessor. At the beginning of this presentation, I'm gonna cover the NOEL-V microprocessor, both its core and architecture. Afterwards, I will talk about the Hypervisor Extension. In particular, I'll give an overview of the implementation, then I'll talk about its details and give a brief description of the verification we performed. And then finally conclude with some concluding remarks. We as a company have been developing space-grade processor for about 20 years. With our Leon Spark processor line, we have always embraced open standards and open source. And we continued this path by adding our NOEL RISC-V processor line to our portfolio. So our NOEL-V processor is a highly configurable RISC-V processor IP. It's a 64-34-bit architecture processor, superscalar, with dual issue in order pipeline, with support for the Hypervisor Extension and fault tolerance. Regarding its performance, it's currently achieving 4.41 core mark per megahertz on the dual issue configuration and 3.05 for the single issue configuration. More information can be available and found on our website. Regarding the NOEL-V architecture, the NOEL-V supports either RISC-V 64 or RV32 as a base architecture, and it also supports a set of extensions like the multiply and division, M, atomics, A, single and double floating point extension, the FD, and also compressed instructions like C, and hypervisor support, now the H. The MMU supports SV39 as well as SV32 page tables with hardware page table walk and separate TLBs for data and instructions. Whereas the memory protection, physical memory protection is also supported. We have that our design is a 7-stage dual issue in order pipeline. We also support the late LUs and branch unit with dynamic branch prediction support. We also support a return address stack. We are currently investigating other extension, so like bit manipulation and vector instructions. Regarding the L1 cache, we have two separate caches, one for instructions and one for data, each with a maximum 4 ways and size of 16 kilobyte with a single cycle access time. Moving on to the Hypervisor Extension implementation, I'll start with a general overview. So our current implementation of the Hypervisor Extension was targeting the draft standard version 0.6.1. However, the implementation will be soon updated to support the latest 1.0.0 version of the standard. This extension transforms the supervisor mode to the Hypervisor Extended Supervisor mode. It also adds virtualization modes, virtual supervisor mode, and virtual user mode. The Hypervisor control status registers are added to extend the S mode with the hypervisor feature. So the virtual supervisor control status registers are added to substitute the regular supervisor registers when running in virtualization mode. Some machine mode control registers are extended, like M status, in order to handle virtualization mode status. Support for some new exceptions and interrupt are added. and 2 new machine mode control registers are also added, in particular the M2Val2 and Minst. They both help with drop handling. Moving on, we have added the support for hypervisor guest external interrupts. This enables direct assignment between the virtual machine and the physical device. And in order to support this, in the interrupt controller we are evaluating the APLIC specification. Regarding the MMU instead, we updated the MMU to support the 2-stage address translation with guest physical TLB. The first stage TLB includes all the information for the complete 2-stage address translation and also information for the NPM check. The 2-stage address translation and the guest physical TLB are only used on a miss in first stage TLB, which then results in a page table walk. Currently, we only support SV39X4 hypervisor page tables. Concerning the implementation impact, our preliminary numbers indicates an area increase around 5%, even though the number also depends on the size of the TLBs used for the second stage translation. Regarding the details of our implementation, the PMP is a less configurable memory protection than having an MMU, but it's cheaper to implement and supports machine mode. So rather than having a trio of pages like an MMU, the PMP has a fixed set of registers that can specify memory areas, which are then protected from read, write, or execution by any code in the supervisor or user mode or even machine mode. In a simple implementation, the PMP checks can be applied after the address mapping via the TLBs, both for data and instruction accesses as well as for any page table walk accesses. So when introducing an hypervisor, however, the extra layer of the TLB lookup makes it nearly impossible to perform all the checks in one cycle. To overcome this, our solution combines checks on the page table walk so that both the TLB layers and the PMP checks can be done by a single lookup. To achieve this, we added a separated hypervisor TLB or HTLB beside the 2 previous instruction and data TLBs. Since we don't need a whole hypervisor page table walk for every element in the supervisor page table, the HTLB improves timing. Moreover, all permissions checking are now done via a single TLB lookup. And finally, we do not need to check the PMP separately for the supervisor TLB, but only the corresponding HTLB entries. Regarding the limitation of our implementation, when there is no MMU active, in order to avoid unexpected delay, we still do PMP checks directly on the physical addresses without any TLB. And currently that limits the ability to do many PMP checks. As a side, we also have a more complex page table walk, as we can see from the final state machine images below. Regarding the verification instead, our implementation has been tested with individual tests, for example, hypervisor instructions and the current status register, 2-stage address translation, and so on. We have also extended our random instruction generator to support the Hypervisor Extension, and we utilize virtualization mode generate hypervisor extension instructions, and two-stage address translation. Lastly, we run tests using hypervisor which already support the H extension, like Xvisor, and we will run Xstratum, which is ported to the NOEL-V in the De-RISC project, and also Jailhouse in the context of the Selene project. We have used Spike as a reference implementation for the H extension in our verification, and QEMU was also used as a reference. In the picture on the right side, we can see that indeed Linux was able to run under Xvisor. In conclusion, we have our NOEL-V processor being a superscalar dual-issue RISC-V, either 32 or 64-bit microprocessor core with the fault tolerance error correction code support. With this work, we have added the Hypervisor extension support. Our current implementation supports the 0.6.1 standard version, but will soon be updated to the latest 1.00 version. And with around 5% overhead, our implementation has already been tested with the Xvisor, and soon with Xstratum and Jailhouse hypervisor from the RISC and Selene project. Thank you for your attention. This concludes my presentation.